Hello and welcome to this presentation related to further transposition, which we consider a formula that's been generated within our mechanical principles unit from an energy balance. Here's the formula we will be transposing throughout this presentation. As I say, it's generated using the principle of conservation of energy we reviewed in a previous presentation. And for your reference, there are previous presentations related to transposition. There's an introduction to transposition, further transposition, and there's also advanced transposition of formulae. So these are all the previous related videos that you might want to review before reviewing the contents of this presentation. And here's an extract from the calculation performed in the previous mechanical principles presentation related to applying the principle of conservation of energy to an angular motion problem. And this was the energy balance generated in this particular exercise. So this balance forms the basis of this presentation. So here's a brief overview of the contents of the presentation. Given the formula shown here, we're going to transpose it initially, torque T, shown here. Next we'll transpose it for the friction couple or friction torque TF, here. Then we'll transpose for the initial angular velocity, omega I, shown here in the first term on the left hand side. Next we transpose for the angle turn through, symbol theta. That occurs in two places within the formula, shown here on the left hand side and here on the right hand side. And finally we transpose the formula for the moment of inertia, symbol I. And once again that occurs in two places within the formula, shown here and here. So full work solutions are shown to these respective transpositions. Note essentially the aim of this presentation is to try and improve your transposition within this particular topic area of mechanical principles. So I will show you my approach for transposing for the variables, but you may find a different, possibly preferable solution based on your knowledge and algebraic skill set. And for your reference, here are the approximate start times related to the various transpositions as stated on this slide, but please note these times are rounded to the nearest minute. Overview continued. We will also use this formula given here. Again, it was generated by applying our principle of conservation of energy, and here we're going to transpose initially for the work into the system labelled W1. Next we will transpose for the moment of inertia I, shown here on the left hand side and also here on the right hand side. And finally we transpose for final angular velocity labelled omega F, and that occurs here on the right hand side within the formula. Full work solutions are shown to all these transpositions. And again, with these solutions, I'm showing you my particular approach to transposing for the variables shown, but you may find your own preferable approach. So let's now commence the first transposition. And here are the approximate start times related to the transpositions shown on this slide. Again, these times are rounded to the nearest minute. So here's the formula we're going to use. We'll just be transposing this formula to make different variables the subject. And probably for reference, I've shown the same formula here, but written in a slightly different way. Sometimes students I find are confused with the fraction of a half, shown here and shown here. I'm just trying to show how you can express the fraction within these particular terms. That's just a reference showing you the different formatting using the fraction. Essentially in this first formula, I'm multiplying by a half, and in the bottom formula, I'm actually dividing by 2. Obviously that's one and the same thing. So let's run through the first illustration. Here we're transposing the formula given for the accelerating torque, capital T. So here's our formula. We want to transpose for a capital T shown here. So I'll just outline the mathematical steps involved. So for the second line, we're simply going to subtract the half I omega I squared term from both sides of the formula or the equation shown here. Notice on the next line, I've factorized on half I. That's common to these two terms, so half I outside of my bracket in the omega F squared minus the omega I squared inside the bracket. And on the next line I simply divide both sides by theta, shown here. Notice the first term related to half I omega is fully divided by theta, and of course the TF theta term here is divided by theta. That's why it's simply TF on this line here. And all I've changed on the final line is to bring the theta from the denominator to the numerator. So instead of dividing by theta in this line, I'm now multiplying by theta to the negative 1 in this line. So we've transposed the equation for T. Next, let's transpose for the friction couple, labelled TF. TF shown here on the right hand side. The first thing I will do this time is to subtract the half I omega F squared from both sides of the equation, shown here. Again, on the next line I simply factorised on the half I, so half I outside the bracket and my omega I squared minus my omega F squared inside the bracket. And next I simply divide both sides by theta. Notice I've used here a different form of bracket. So I'm dividing totally the left hand side by theta, shown here. Next I simply turn the equation around, so TF moves from the right hand side to the left hand side, and on the right hand side I've simply shown the half I omega I squared minus omega F squared term plus my T theta, now all multiplied by theta to the negative 1. I multiply both terms by theta to negative 1, so essentially expanding my bracket here. I find that TF is equal to the half I theta to negative 1 multiplied by our bracket containing the omega terms, and I'm simply adding the T term. Because considering this term on its own, the thetas will cancel. So I've rearranged for the friction torque TF. Next I'm transposing for the initial angular velocity omega I shown here. To outline the steps involved in the transposition process, firstly I subtract the T theta term from both sides of the equation. Next I multiply throughout by 2. Notice I have 2 here on the right hand side, and note the use of the bracket. And again, if it helps with your understanding, I'm multiplying both sides by 2 because the half written here of course could be written in this format, and it's sometimes easier to understand why we multiply throughout by 2 when the 2 is shown in the denominator. As I say, just another way of writing this term here. And on the next line I simply divide throughout by I. On the next line I simply remove the I from the denominator, brought it to the numerator, so it becomes I to the negative 1. On the next line I multiply throughout by I to the negative 1, so notice the I for the first term here cancels, so it's just omega F squared. And I've also factorised these two terms here onto theta, so 2 theta in bracket TF minus T, still multiplied by I to the negative 1. So the expression on the right hand side here equals to omega I squared, but of course it's omega I I'm trying to find, so square rooting now both sides of the equation, we find omega I on the left hand side equal to square root of this bracketed term. On the final line I've simply written the omega I is equal to the bracketed term, but raised to the power of 0.5 or half, instead of showing the square root sign. So these are the same equations. Here we're transposing for angle turn through, theta. Note theta occurs in 2 locations within the formula on the left hand side and the right hand side. So essentially we're going to transpose the equation to have the theta terms onto one side of the equation, which we will then factorise on theta, then divide throughout by the bracket. So let's have a look at the steps for this. So on the next line here I subtracted TF theta from both sides, and I subtracted the half I omega I squared from both sides. On the next line I can simply factorise on theta, now showing the torques inside the bracket. On the next line I simply divide both sides by the bracket of torques here. So now we have our formula theta, and the final line I've just shown the formula for theta with the torque bracket moved from the denominator to the numerator. We're just showing it to the power of negative 1. So again, these two lines are essentially the same. They're slightly different formatting. Here we're transposing for the moment of inertia, symbol I. And again, as with the theta terms, note that the variable I occurs on both sides of the formula. So on the next line, first step is to subtract the half I omega F squared term from both sides and subtract the T theta from both sides. Next line I factorise now on the half I, leaving the omega squared terms inside the bracket. Next line I've multiplied throughout by 2, and I have half multiplied by I, so to remove the half here I will multiply both sides by 2, that's shown here. Notice I put the torque theta terms in a bracket. Must ensure I maintain my BODMAS precedent rules throughout the transposition process. Finally, to find the moment of inertia I simply divide both sides by the bracket of omega terms here, and the final line I is equal to the same expression on the right hand side, but instead of dividing by the bracketed omega terms are now multiplying by but raised to the power of -1. So these two lines are essentially the same. This slide now shows a further formula that we generated by applying the principle of conservation of energy in our mechanical principles presentation. And firstly, we're going to transpose this equation for the work done, labelled W1 on the left hand side here. This is actually a relatively straightforward transposition. On the second line here, I simply subtracted the half mu squared term from both sides, and I've subtracted the half I omega I squared term from both sides, from which we find the subject now is W1. All that's happened on the final line is that I've factorised the linear kinetic energy terms on half m, so that's this term here, the half m v squared and the half m u squared term. I've also factorised on the half I for the final angular kinetic energy term here and the initial angular kinetic energy term shown here. So this final line just shows a slightly factorised format for W1. So again, we're considering this formula generated from the conservation of energy, but this time we're transposing for the moment of inertia I. I is located here on the left hand side and here on the right hand side. So again, the essence of the solution is to move all the I terms to one side of the equation, the left hand side in this case, and all other terms to the right hand side. Then we'll factorise the left hand side and then rearrange to make I the subject. So let's consider the process. On the second line here, on the left hand side, I've subtracted the half I omega f squared term from both sides, and I've subtracted the half mu squared term and W1 from both sides. Next line I've factorised on the half I, leaving the omega terms inside the bracket. And the next line I've multiplied throughout by 2. Again, notice the bracket has been used for the terms on the right hand side here. Very important to have the bracket. It means every term in the bracket is multiplied by the 2, which of course they are. And on the next line, to make I the subject of the formula, I simply divided throughout by the bracketed omega terms here. The final line for I just shows the bracketed omega term raised to the power of -1. So these last two lines are essentially the same. And I'll just leave you the final transposition to review if you want to. It relates to transposing for final angular velocity omega f. Omega f occurs here. I'll let you wander through the solution at your own pace. It's continued on the next slide. So still transposing for the final angular velocity omega f. We end up with two formulae for omega f, one shown here, square root of this square bracketed term, and an alternative form for omega f shown here. This is where the I to -1 term here has been taken outside of the square root term. So it becomes I to -1/2, -0.5 here. And instead of the square root symbol here, outside the square bracket, I shall simply raise the square bracket to 0.5 for my final line. So there's a few transpositions trying to show you how we manipulate the energy balances we generate in our previous mechanical principles presentation, which I know some students do struggle with. I hope this presentation has been of use to you, and as always, thank you for viewing.